The Large Hadron Collider lies in a tunnel below the border between France and Switzerland. A magnetic field 100,000 times stronger than Earth's bends the paths of charged particles emerging from high-energy collisions. The curved tracks of these particles reveal their mass, charge, and energy.
Meanwhile, high above our planet, Earth's magnetic field deflects charged particles coming from the sun and outer space. What is this invisible force that controls charged particles moving near the speed of light, directs the flow of matter in the cosmos, and creates a magnetic cocoon protecting life from the sun's deadly radiation? Our star, the Sun, is the solar system's source of light and heat, driving Earth's climate and bringing our planet to life. Magnetism channels the paths of hot ionized gases climbing upward from the Sun's visible surface. These sunspots look harmless, but most of the Sun's dramatic and potentially lethal eruptions begin in these active regions. Gases flow along these glowing arches. They rise up from the sun and then fall back, still trapped by the sun's gravity and ruled by its magnetic field. The sun's magnetic fields get tangled. Usually, the sun's gravity pulls these prominences back to the sun. But if the magnetic field is twisted enough, the arches can break, releasing streams of hot gases into space in a CME, or coronal mass ejection. If this CME is headed toward Earth, a violent blast of charged particles will slam into our protective magnetosphere in a day or two. Earth's magnetosphere has cracks caused by magnetic reconnection. The solar wind pulls reconnected field lines into the Earth's magnetic tail. These stretched field lines ultimately connect again, blasting charged particles into Earth's upper atmosphere and resulting in shimmering auroras near Earth's poles. The aurora borealis, or northern lights, occurs most often along a circular zone across central Alaska, Canada, Greenland, northern Scandinavia, and Russia. Because the magnetic tail is on the night side of Earth, the most intense, dynamic, and beautiful auroras occur near midnight. The low orbit of the International Space Station keeps it within Earth's protective magnetic field. In early 2016, astronauts gathered in the cupola, their favorite place to watch the Earth below. Anxiously, they looked northward, hoping to see and photograph an aurora. As their path crossed over Europe, they captured an aurora's green light along the northern horizon, dancing above Scandinavia. Gradually, it faded from view as their path moved southward over the Black Sea. Meanwhile, for the first time, a crew in Tromsø, Norway, photographed the same aurora from the Earth's surface.
The aurora is a mysterious and unpredictable display of ghostly lights in the night sky, an eerie sign that our planet is electrically connected to the sun. Auroras can appear as long, narrow arcs extending overhead from horizon to horizon. From the side, they look like ribbons that kink, fold, and swirl. Their flickering rays align to the Earth's magnetic field and ruffle like curtains in an imaginary wind. They can also spread out like a heavenly crown, engulfing the sky in a misty veil. In an auroral substorm, sheets twist into waves and curls. Our ancestors saw great dragons or serpents in the sky. In northern Europe, the aurora was the famous Bifrost, a glowing archway of the gods to travel from heaven to earth. In America, they were spirits carrying lanterns as they sought the souls of dead hunters. Auroral rays follow the lines of force in Earth's magnetic field. Oxygen atoms emit a green light when hit by high-energy electrons. Low-energy electrons higher in the atmosphere cause oxygen atoms to glow red, giving the green aurora its red tip. These wispy auroras show us that our magnetic shield is still intact. When high-energy electrons strike nitrogen atoms, the atoms produce blue auroras at high altitudes and sometimes magenta auroras at low altitudes. The blending of aurora colors can produce purples, yellows, pinks, and whites. When you see auroras from the side, you can tell that the different colors come from different heights in the atmosphere.
This diffuse blood-red aurora spreads over the sky. During strong solar storms, these enormous red glows occur as far south as Florida and Texas. Auroras of all colors are signs that our planet is a life-bearing world, with an atmosphere of oxygen and nitrogen protected within Earth's magnetosphere. For centuries, sailors recognized that the star Polaris hovered very close to the north point in the sky. Patterns like the big and little bears encircled this North Star. Explorers could sail the northern oceans by observing the position of Polaris in the night sky. But on cloudy nights, they needed another device to chart their course. The magnetic compass reached Western Europe in the early 13th century. With it, sailors could cross the planet's great oceans, discovering Earth's size and mapping its continents. Earth's uncharted lands became places on a map. Its coastlines defined a world far larger than early sailors had imagined. The generator of Earth's magnetosphere lies deep in the planet's core. Here, currents of liquid iron rise and turn with the Earth's rotation. The resulting electric current in the moving molten iron generates Earth's magnetic field. This field, in turn, reinforces the currents that created it. The result is a geodynamo, giving Earth its magnetic shield. This geodynamo turns Earth into a large bar magnet with north and south poles. We can see a bar magnet's magnetic field by dropping iron filings on a piece of paper above the magnet. The filings line up with the direction of the magnetic force. Earth's magnetic field has these same lines of force connecting its north and south poles. Creating this global magnetic shield required special conditions. Earth had to be large enough to have a molten core and had to rotate fast enough to produce an electrical current that generates the planet's magnetosphere.
Many different animals can sense Earth's magnetic field through structures in their eyes or brains. If fish swim along the direction of Earth's magnetic field lines, they sense nothing. But if they swim across the magnetic field, they can detect a tiny electrical force. This force guides them as they migrate north and south during the year. Hammerhead sharks have special gel-filled organs called the ampullae of Lorenzini, which detect electric fields, both natural fields and those created from swimming across magnetic fields. Sensitivity to magnetic fields helps sharks and other fish swim in straight lines across the open ocean.
The floor of the Atlantic Ocean tells us that Earth's magnetic field has not always been like it is today. A ridge runs from north to south in the Atlantic Basin. Here magma flows upwards, spreads out, and turns into iron-rich rock. Like iron filings, the iron atoms in this rock are oriented to Earth's magnetic field at the time the rock hardened. From their changing orientation, we know that Earth's magnetic poles have flipped many times in geologic history. Currently, Earth's magnetic field is decreasing in strength each decade. There could be a reversal of Earth's magnetic poles soon, perhaps in the next 1,000 years. Our advanced civilization depends on electromagnetic fields in communication, transportation, electricity production, and power distribution. When the poles flip, the Earth will be temporarily without its magnetosphere. Astronauts and aircraft passengers could be grounded because there is no magnetic shield to protect them. The next magnetic pole reversal may be destructive and deadly. In March 2015, NASA launched a mission called the Magnetospheric Multiscale, or MMS, aboard an Atlas V rocket. Its mission is to observe the conditions that allow charged particles to penetrate Earth's magnetic shield.
The main engine start. 3, 2, 1, 0.